thermodynamics. Now, there are two words in this. One is therm and one is dynamics. Dynamics means mechanics and therm means heat. But before we go into the chapter of thermodynamics, we have to understand a few terms. The first term you can write external properties. First term is external properties. Now, examples of external properties can be, you have already learned these things in mechanics: position, suppose displacement, velocity, then acceleration, etc. They are all external properties of a body. Now, why external? Because from them we get an information about the nature of the body. They are discussed, already discussed in the subject of mechanics. So external properties are related to which subject, which part of physics? That is mechanics. Now, second point is internal properties. Internal properties. Now, what do we mean by internal properties? Properties, let me give you a few examples: mass, then volume, pressure, temperature, density, etc. Mass, volume, pressure, temperature, density, etc. They are known as internal properties of a body. Now, we have heard the word macroscopic or bulk, bulk, bulk. These are bulk or macroscopic properties, and they can be measured by simple experiments. They are macroscopic, not microscopic. Macroscopic property or bulk properties that can be measured by simple experiments. Any change in these properties generally involves transfer of energy. Now, this phrase is very, very important. Transfer of energy in the form of heat or work. So, I am going to write the sentence for you. So, I have written two lines here. These properties, they are called bulk properties or macroscopic properties, and can be measured by simple experiments. Any change in these properties, that means in these bulk properties or macroscopic properties like mass, volume and pressure, generally involves transfer of energy in the form of heat and work. Now, heat and work, the term thermodynamics has two words in it. One is a heat, that means therm, and dynamics means work. So in simple words we can say that it is a relation between heat and work. Now, you can call this is this branch of physics which relates heat and work, is known as thermodynamics. That means heat as an energy is converted to work, and when we do work, heat is produced. So interrelation between these two things, termed as one or coined in one term, called thermodynamics. So, in other words, we can say that these properties, or rather the internal properties, can be also called thermodynamical properties of matter. Now, this thermodynamics subject is completely based on experimental data, and every thermodynamic formula comes from the analysis of the data. For example, suppose a fixed mass of an ideal gas is studied at constant temperature. I repeat, a fixed mass of an ideal gas, fixed mass of an ideal gas. So the mass is kept constant here at constant temperature. Any change of pressure produces a change in volume, and different sets of P and V are obtained. Any change of pressure produces a change in volume, and different states of P and V are obtained. Now, temperature remaining constant, pressure changes with volume. You have already studied in the part of Boyle's law. An analysis of this measured values shows that the product PV is equal to constant. Now PV is equal to constant means it is a complete Boyle's law statement. This is a well-known Boyle's law. This is a well-known Boyle's law statement. It is actually a thermodynamical law, as this is experimentally based. As this is experimentally based, it is a thermodynamic law. So Boyle's law is, or we can call it a thermodynamical law. Now we start with the topic of thermodynamic systems. Now you have to study 3 or 4 types of systems before we delve into the main subject. A body or a part of a body, or a part of a body, or a combination of a number of bodies is usually called a thermodynamical system. I repeat, a body, part of a body, part of a body, or combination of a number of bodies. That means it can be one single body, it can be a part of a body, or it can be a combination of any number of bodies. This is called a thermodynamical system. Now the main property of a thermodynamical system is, or rather the field of a thermodynamic system is that it interacts with its surroundings. That means it has a relation with the surroundings or environment. You will find these two words. One is surroundings and another one is environment, the same meaning, and exchanges energy and mass. That means what we can write, such a system interacts with surroundings. The word surroundings and environment both can be used. Environment, and exchanges energy and mass. Now these two terms are very important. Exchanges energy and mass. The environment or surroundings includes all external objects but have some influence on the system. For example, if a room in a house is considered as a system and its thermal properties are to be studied, the sun at a distance of 10 to the power 8 kilometers or something like that is an important component of the environment, but another house only 100 meters away need not be included as a component. I repeat, if a room in a house is considered as a system and its thermal properties are to be studied, the sun at a distance of 10 to the power 8 kilometer is an important component of the environment, but another house only 100 meters away need not be included as a component. Thermodynamical systems are of 3 types. Thermodynamical systems are of 3 types. Now you have to understand these types very well, because these 3 types control the full chapter. First one is an isolated system. Second one is a closed system, and the third one is an open system. Now what is an isolated system? That means there is a system, that means a body or a number of bodies, that is completely isolated from the surroundings. That means no transfer, that means no energy, no mass. That means it does not exchange any energy or mass. So what does it does not exchange energy or mass with the surroundings? You can write with the surroundings. Now second one is a closed system. Now, there is a little bit link between the isolated system and the closed system. It will seem that the two words are same, but there is a slight difference in meaning, because here there is no exchange of energy, no exchange of mass, but for closed system energy is exchanged but mass remains fixed. So energy is exchanged but mass remains fixed. Now the third system is an open system. As the word open, the meaning of the word open means both energy and mass are exchanged. Both energy and mass are exchanged. Now properties like number of molecules, molecular velocity, such properties are called internal microscopic properties. I repeat, internal microscopic, not macroscopic. Microscopic properties of a body, they are not directly measurable and experimental data is absent because they are internal properties. As these properties are internal, we cannot directly measure it even by experimental basis. Hence the study of this subject is based on theoretical assumption. So you have to assume, and this is known as the kinetic theory. The next chapter after thermodynamics is kinetic theory of gases, in which we are going to deal with the internal properties of matter. Such matters like examples I have just given, number of molecules, molecular velocity, etc. They are internal parameters which will be discussed in the kinetic theory of gases. Now, nature of heat. So first we are going to see in thermodynamics what is the definition of temperature. Now, definition of temperature comes earlier from the zeroth law of thermodynamics. The definition of heat is based on the concept of temperature. So what is heat? We all know, you have studied it earlier. Heat is a form of energy which flows between different bodies due to the temperature difference only. So two bodies I have taken, temperature T1 and T2. Temperature T1 is greater than T2, so we know that heat is going to flow from the first body to the second body. So we define that heat is a form of energy which flows between different bodies due to their temperature difference. The temperatures are not same. Now, up till which time that the heat will flow? When the bodies will have got the same temperature, balanced temperature between the two, the heat will stop. The heat flow will stop. The heat flow will stop. So in SI unit we know that energy is directly used to measure some quantity of heat. In joule is the unit of heat here. We will learn about calorie, relation between joule and calorie. Immediately it becomes clear that the energy units must have definite relations with the conventional units of heat. That means relation between heat and work. From the first word I have said that relation between heat and work. Now instead of work I can pronounce energy also. So it is a relation, definite relation with the conventional units of heat. So we start with Joule's law. What is Joule's law? If some amount of work is entirely converted into heat, then the work done and the heat produced are proportional to each other. That means, I repeat, if some amount of work is entirely converted to heat, that means work and heat are proportional. Work and heat are proportional to each other. W is the work done, H is the heat. Now instead of proportionality sign, if we place an equal to, we have placed a proportionality constant here, which is termed as J, H. This J is known as the mechanical equivalent of heat, W by H. So J is known as the mechanical equivalent of heat. That means work has been converted to heat. Mechanical equivalent means, mechanical means work, equivalent quantity of heat is produced. That means energy in the form of mechanical energy has been converted to heat energy. This is known as the mechanical equivalent of heat. Now the values of the mechanical equivalent, you can state here 4.2 joules per calorie. Now, why joule per calorie? Because work is measured in joules and H standardly we take it to be in calories. So 4.2 joules per calorie. Now, if we take both the units to be in the CGS unit, this is the SI unit, this is the CGS unit of heat. So if we take both the quantities into the CGS format, that means joules, we have to convert it to ergs. So 10 to the power 7 ergs per calorie. Now this format and this format you have to learn, and you have to tactically use these values in the problems, because when you are converting heat into work using this relation, then a difficulty will arise in placing the units of these two things, work and heat. You have to put, if you replace 4.2 here, then you have to state W or work in joules and heat in calories. But if work is in ergs, then J should be written as 4.2 10 to the power 7 ergs per calorie. Now, to avoid this discrepancy, you will always try to do the problem in the CGS format. If you do in the SI on the SI style, then you will fall into trouble. So we will try to do it in the CGS form. From this 4.2 joules per calorie, we can also say that to produce 1 calorie of heat, 4.2 joules of work must be done. That means 4.2 joules of mechanical work done produces 1 calorie. Work converted or energy converted, mechanical energy converted to heat. Now we take one problem. Suppose water drops from the height of a 50 meter in a waterfall. Now this is a waterfall. The fall in height is 50 meters. Water is falling from this height to 50 meters down. Find out the rise in temperature of water. Now the temperature here is suppose T. This temperature, when the water has fallen a distance of 50 meter down, the temperature of this water will be higher than that of the top. Now if 75% of energy is converted to heat, what happens? And absorbed by the water. Now you all know that when particles fall from a height, there will be a shift in its potential energy. So W we can write mgh, where h is equal to 50 meters. That means that it is a decrease in the potential energy, which will be converted to an increase in the thermal energy. Now 75% of this energy has been converted to heat. That means W is equal to JH. If we apply this formula that we have studied from Joule's law, W is equal to mgh into 75%. That means mgh into 75% is equal to joules J into what is H MST. From calorimetry you all know H is equal to mass into specific heat into temperature change. So J is equal to MST. Now in the previous part, as I was explaining, that you have to do the problems in the CGS format. If you do not do that, you will fall into trouble. Now what trouble? If we eliminate the two masses M from both the sides, then you see that this M is in grams CGS, because the unit of heat is in calories, and this M is in SI system. You cannot eliminate this 2m. Even if you find the 2m's, you will not be able to deduct or cross this 2m's, because one is in CGS unit and one is in SI unit. So to prevent the mistake, we have to see that we can do the problem totally in the SI system. So we will replace J as 4.2 into 10 to the power 7. Then only we can eliminate these two M's. Into M, now what is S? S in for water it is 1. You all know the specific heat of water is 1 calories per gram per degree centigrade. S is equal to 1 calorie per gram per degree centigrade, per degree centigrade. So 1 calorie per, so in this mgh into 75 by 100. Now what is the value of G? That is 980. So M into 980 into 50 meters. We will not write 50, we will write 50,000, converting that into centimeter by 75 by 100 is equal to 4.2 10 to the power 7 into M into 1. Now you can eliminate these two M's because both the sides of the equation are in CGS system. Hence you can eliminate these two M's now. Now after calculation of this, missed out on T here. So you have to find the value of T here. After you have calculated, I have done with the help of a calculator 0.0875 degrees centigrade. Now thermodynamic process. Now in this category you have to study the different types of process that you are going to face while solving the problems, namely isochoric process, isobaric process, isothermal process, adiabatic process. Now what is a thermodynamical process? First of all, if we say that the system be initially at an equilibrium state A, this is an equilibrium state A. Now if the system exchanges energy in the form of work or heat, anyone, either work or heat, that means the term that we have to keep in mind always is the exchange of energy. Thermodynamic process every time is the exchange of energy between the body and the surrounding. So if a system exchanges energy in the form of work or heat with the surroundings, then the values of, suppose, volume, pressure, temperature, the basic parameters you have to endure with, volume, pressure and temperature would change. Now in general, the system would deviate from the state A. This system is going to deviate from the state A. Now suppose it moves to another state B. Now how did it move into another state B? When the energy exchange stops. When did it move into state B? When the energy exchange stops, the system would attain a very new equilibrium state, that is B. So A was an equilibrium state. From that, if it exchanges energy, it moves or shifts from its equilibrium position because of a change of Vp and T, volume, pressure and temperature, attains a new thermodynamical state or thermodynamical equilibrium state, that is B. The transition of a system from initial state A to the final state B is known as the thermodynamic process. So in simple words, I repeat, the transition of a system from an initial state A to the final state B is known as the thermodynamical thermodynamical process, and is usually denoted as A direction B. It should be noted that the transition between two states may occur only, transition between two states may occur along different paths also. Now this is path 1, process AB. You can follow another path also. So you can write A to B by process 1, again A to B by process 2. That means the path is separate. Now what separate path means? The process is also separate. So this path and this path are separate paths, signifying that we are dealing with two different processes. The first process we know is isochoric process. Now this process, as the name goes, isochoric means the volume is constant. What is constant? Volume is constant. in this process. Both pressure and temperature undergo some changes. The second process, you have to just learn or remember what is constant, which parameter is constant. Now for a isobaric process, bar means pressure. Pressure is constant. Number 3, you can say isothermal process. Now what is therm? Therm means heat. So here temperature is constant, temperature T is constant. And the last one, you can say adiabatic process. These are the 4 processes you have to handle here. Adiabatic process, why adiabatic? The heat exchange between the system and its surroundings remains zero. That means no exchange. No exchange means nothing. Okay, so the heat exchange between the system and the surroundings remains completely zero. They are changes to all of Vp and T. That means one thing you have to keep in mind while studying this last one, adiabatic, that means there will be no exchange of heat from the surroundings to the body. That means from the body to the surroundings or from the surroundings to the body.